So thank you to Holger and Massimo. I'm sorry I couldn't join you yesterday. I was indisposed, as they say, and I'm feeling a little bit better today. So let's see how we go. So it turns out that quite a lot of what I'm planning to say has been said, I think by Francis and probably by Jean-Luc and Simon yesterday. But maybe the perspective is a little bit different, and the colors are different, and the font's different. And it probably doesn't hurt to hear it more than once anyway. So I hope that you'll bear with me if you've some of this stuff seems familiar. So what I'll talk about mostly in this talk is about formulation rather than solution. In the next lecture, I'll talk more about solutions, algorithms, which is more along the lines of what Francis talked about this morning and also yesterday. So today I'll talk about problems and how they're written as optimization problems. So our goal really essentially is to do inference via optimization. So many inference problems in all of these different areas: image reconstruction, image denoising, signal reconstruction, supervised learning, unsupervised learning, statistical inference, and so on. A lot of overlap between these areas, but many of these can be written as optimization problems. And here's kind of the standard general form of what happens. You make some observations about some data. There's an object, we'll call that Y. There's an object that you're trying to recover. Let's call that X. That's what you're trying to get out of the reconstruction process. And there's some sort of criterion, G, which is a function of X and Y. And given the Y, you want to find the X that minimizes G. And that turns out to be the one that you're looking for, or at least an estimate of the one that you're looking for. So G is the inference criterion, and the big question is, well, how do we find G? Where does it come from? What principles do we use to build a G that will give us the right answer? And the answer is it comes from the application domain. And there's many, many, I gave you a large variety of problems on the first slide that fit this format. And the G is going to be different depending on which domain it comes from, whether you're doing machine learning, signal processing, system identification, computer vision, bioinformatics, and so on. Many, many areas. And I'll give a number of examples in the rest of this talk. Okay, and just to emphasize what we're doing here, in minimizing G with respect to X, we're seeking the X such that G of X and Y is less than or equal to G of Z and Y for all other possible choices of Z. Okay. And then how we solve the optimization problem, and then we'll say more about that during the rest of today. Okay. So very often, G has this kind of a structure, and this came up in Francis's lectures as well. It's got two terms. The first term we'll call H, depends directly on Y, and the second term doesn't depend on Y. Okay? The first term is a measure of how well X fits or explains the data Y. So Y is a set of observations that you've made, and H is like a fitting function. You can call this it goes by a number of different names. Loss function, observation model, data term, log likelihood, as we'll see in a moment where that comes from. Okay, so this measures the fit between X and Y. And the second term is often called a regularizer, and it somehow captures the prior knowledge of X, the plausibility of X, also known as the generalizability. And this is the term, as Francis says, this is the term that helps you avoid overfitting to the data. If you don't have the psi here, or if tau equals 0, then you'll do a very good job at fitting the data that you see, but you may not do such a good job of fitting the data that you don't see. And so it's important to include this term to sort of take account of the data that's not observed in the empirical model. And so tau here is a parameter, it's a real number that captures the trade-off between these two terms, the regularizer and the fitting term. So since the Y is fixed for purposes of this problem, we often just leave it out of the formulation and just write down the objective as a combination of the fitting term and a weight times the regularizer. Okay, so how does this come from statistical models? Well, very often that you've got a likelihood model. Given what's the likelihood of observing Y given an X? The X, of course, is the thing that you don't know. But suppose you did know it, what's the likelihood of observing Y? Very often you can write down that likelihood in this form as the exponent of the negative of some function, H of X and Y, some joint probability function, divided by some normalizing term. Okay? So often this is the probability of seeing y given x. The prior probability of x, might be given by some other term. It might be the exponent of minus tau times some other function of x, again divided by some normalizing term. So using Bayesian principles, the probability of observing, the probability that x is the thing you're trying to recover, given that you've observed y, using Bayes' law, is given by this expression here. Probability of y given x times p of x divided by the probability of y. Okay? So if I take the log of that term, I'll end up with something that's exactly of the form that I've had on the last few slides. The log of p of x given y will simply be the log of p of y given x, which is just going to be minus h of xy, plus the probability of plus log of p of x, which is going to be minus tau times psi of x. And then everything else is stuff that doesn't depend on x. So I can basically leave it out. These constants will show up there, and also the p of y, which doesn't depend on x. So if I just focus on the part that depends on x, I end up with just this g of x and y. Okay? Now here we're usually seeking the x that maximizes this probability, whereas in optimization we usually think in terms of minimization. So that's why instead of trying to maximize minus g, which is what I do if I maximize this log posterior distribution, I try to minimize g. Okay, and of course it's the same thing. So often the x that we're looking for is a maximum a posteriori estimate. So this is the Bayesian derivation of this MAP principle. Okay. So let's look at the forms of this unknown x. Very often you can write it as a vector of some kind in some formulations, and I'll give some examples later on. It's more conveniently expressed as a matrix. What sort of regularizers? I talk a lot about regularizers in this part of the talk. What sort of regularization functions are we looking for? Very often we're looking to make the matrix or vector sort of small in some sense, to suppress its size, not let it blow up too much. Another thing we often like to do with this solution is to impose some sort of sparsity on it to make sure that it consists mostly of zeros, just a few non-zeros scattered around the place. Sometimes we also try to impose specific kinds of non-zero patterns. So we don't just want it to have few non-zeros, but we want those non-zeros to maybe occur in clusters or to follow some sort of pattern. In the case of a matrix, we might want to impose some sort of low rank on the matrix, or we might want to impose some sort of smoothness or piecewise smoothness. So if x represents a function or parameterizes a function, we might want to make sure that that function is not too rough. This, of course, the same thing when you're trying to do spline fitting. You often try to impose smoothness properties on the spline you recover. Okay, now there are different kinds of combining the data fitting term to the regularization term. And the one that I've talked about so far, sometimes it's called Tikhonov regularization, where you actually write down an objective that's just a combination of the data term and the regularizer. But there are other things you can do, and my colleague Mario Figueiredo came up with these names. Obviously he dug into the literature a little bit, and he noticed that one other way that you can formulate this problem is to minimize the regularizer subject to some threshold on the data term. Okay? You require the data term to be below some threshold epsilon. Or you can go the other way around. You can minimize the data term subject to the regularizer being less than some threshold. Now, it turns out that very often in the literature you'll see these other two formulations being used, but in fact they're all sort of equivalent. There's, in some sort of semi-rigorous sense, you can show that these things are all roughly saying the same thing. And in fact, you can actually use indicator functions to write them rigorously, to write the second and third one rigorously as the first one. Okay, but in some terms, it's easy to prove things about things that are written in these forms than it is to prove things about the Tikhonov form. But you should bear in mind that if you can prove something about one of these forms, it usually says something about the first form as well. Okay. So a quick review of norms. I think this is probably something that you're all totally familiar with, but I thought it wouldn't hurt to have a slide about it. A norm is simply a function that maps a vector space to the set of real numbers. in fact, a set of non-negative real numbers. And it has three basic properties. There's the homogeneity property. If you take the vector x, multiply it by a scalar, the norm gets multiplied by the absolute value of the scalar. It satisfies the triangle inequality. So if you add together two vectors in the vector space V and take that norm, that's less than or equal to the sum of the norms of the two individual vectors. And the third one is that the only vector that has norm 0 is the 0 vector. Okay? So if you've got a vector that's not 0, then it's guaranteed to have a norm that's positive. All right, they're the key properties of a norm. And here are some useful examples. One is that if the vector space happens to be the vector space of Euclidean, of real vectors of length n, then there's a so-called LP norm where you sum up the components of x raised to the power p and then take the 1 over p root of that. Of course, the special case where p equals 2 is very important, and p equals infinity, p equals 1. The limit as p goes to infinity of this is simply the maximum absolute value of the elements of x. And the 2 norm, I mentioned also the Euclidean norm. The 1 norm is just the sum of the absolute values of the elements of x. When you're talking about matrices, it's useful to think about the nuclear norm. That'll come up again a little bit in some of the examples I do later. So the nuclear norm is simply the sum of singular values of x. If x is symmetric, if x is n by n, we can write this as the trace of the square root of x transpose x. That's the same thing, sum of singular values. Okay? This is helpful when we're trying to find low-rank solutions. This kind of a norm suppresses the rank of the matrix. And another important case that's not a norm is when you take this expression here and let p go to 0. Okay? And what happens then? Well, what happens then is that this expression goes to the so-called cardinality or the 0 norm. That it approaches the it approaches the number of non-zeros in x. Okay, the number of non-zero elements in x. And very often that's what we're looking for. If we're trying to impose sparsity on a solution, we're looking for a solution with a restricted number of non-zeros. Okay? The problem is that this is not a norm. It doesn't satisfy those expressions I had earlier on. Okay. In fact, it doesn't satisfy the first one here for a start. If I take a vector with a given cardinality and multiply it by a scalar, its cardinality doesn't change. Okay? But its norm is supposed to go up, and so it's not going to satisfy that first condition. All right, here are some pictures of norm balls. So if we're dealing in 2 dimensions, R2, it's very easy to see what norms look like. This is the blue line here is the set of points in R2 that have a 1 norm of 1, okay? Where the 1 norm is 1. That is the absolute value of x1 and x2 sums up to 1. This one is where the set of points where the 2 norm is equal to 1. That is x1 squared plus x2 squared is equal to 1. And this is the set of points where the infinity norm is 1. That is the maximum of x1 and x2 absolute value is equal to 1, okay? When we go to 3 dimensions, the diamond is still a diamond, but now it's a 3-dimensional kind of diamond. So the surface of this object here is the set of points where the 1 norm is equal to 1. And then, of course, the ball stays a ball. So if we're using the 2 norm, the surface of the sphere is a set of points where the 2 norm is equal to 1. All right. So let's think about, I'm going to start talking about recovering sparse solutions of underdetermined systems now, which is something that I'm sure Simone and Jean-Luc probably talked about a bit yesterday. But let's suppose I've got an underdetermined system. I'm given a set of measurements y, and I know that I got y by taking a times some vector x. But this matrix A has fewer rows than columns. Okay? M is less than n. It's an underdetermined system. So there doesn't seem to be enough information here to recover x. We don't have enough elements in general to recover x. We can do, to get something with a unique solution, we can try to recover, we can try to find the least norm x that satisfies this constraint. So we can write down an optimization problem, which is to find the x with minimum 2 norm that satisfies this constraint. And we can write down in closed form what the answer to that is. Okay? The problem with that is it may not be the answer that we're looking for. There's a whole manifold of x's that will satisfy this condition. and I've just picked out one of them here, the chances are it's not the one I'm looking for, unless we're very lucky. Okay? So how do I actually find the one I'm looking for? Well, you have to tell me more about what I'm looking for here. Okay? But often we may, the one that we may be looking for might be the one with, say, a certain specified maximum number of non-zeros. Or it might be the X that satisfies this condition with the minimum number of non-zeros. Okay? That might be the one that's most useful to us for whatever reason. And so this might be the optimization problem that we really want to solve. The problem with this optimization problem is it's too hard. Okay? This is not even a convex problem. It's not even continuous here. As we pointed out, if you take a vector with a certain cardinality and you take one of the 0 elements and just tweak it a little bit, the cardinality is suddenly going to jump by 1. Okay, so the function will jump, and it's not a nice problem to solve. Okay. Now, a little bit about convexity. Now, convexity has already been mentioned a whole lot of times, but I thought I'd define terms here as well. When we're talking about convex sets, the key property is if I take any two vectors in that set, then everything on the line joining those two vectors also has to be in the set. So here's an example of a non-convex set where the line goes outside the set. If you've got a strictly convex set, then given any two elements in the set, every element on the line joining those two elements is strictly inside the set, in the interior of the set. We call that strictly convex. Here's an example of a set that's convex but not strictly convex. It's basically got a flat edge. When we're talking about functions, we can think in terms of extended real value functions. We don't have to insist that the range of the function is the reals. It can be the reals including plus infinity. Okay? So plus infinity is allowed to be in the range. That's useful when we're defining the functions to include indicator functions of sets, for example. So first of all, it's a proper function if it's, if it makes any sense. Proper functions are those where the domain, the set of points where the function value is finite or infinity is, where the set of points is the set of function values is finite, is not empty. Okay, so it has some finite values in its range. The function is convex if it looks like this. Okay, if you take 2 points, x and x prime, and you look at the function value on the line between those 2 points, okay, that function, the graph of the function lies below what you get by just interpolating the function linearly between those two endpoints. So the left-hand side of this expression is given by the function graph here. The right-hand side is just given by this linear interpolant between f of x and f of x prime. And as you can see, the true function lies on or below the linear interpolant. Okay? Now it's strictly convex if this is the situation, if the function is strictly below the linear interpolant, everywhere except at the two endpoints. Here's an example of a function that's not strictly convex, where it's got a flat piece here. And so there are points between the two endpoints where the function is equal to the linear interpolant. Okay? Now, lower semi-continuity turns out to be an important concept here. Lower semi-continuous functions are one where if you're creeping towards some point x0, and you're trying to look at the limit of the function values as you approach x0, it might suddenly jump down when you actually get to x0. Okay? It may not be continuous. If it were continuous, then this would be an equal sign, but it may jump down. Okay? It's not allowed to jump up. So that's called lower semi-continuity. So here are two functions here. This one is lower semi-continuous, okay? Because when you creep towards 0, if you're creeping towards 0 from this side, it suddenly jumps down to here when you get to 0. If you're creeping towards 0 from this side, it's continuous. Okay? This one is not lower semi-continuous because when you're creeping towards 0 from this side, it suddenly jumps up to this function value. Now, why is this an important concept? Well, one reason is that the epigraph of a lower semi-continuous function is closed. So the epigraph of a function, if I can use the board briefly, the epigraph of a function f is just the set of points x and y where y is greater than or equal to f of x. Okay, so if I have a function that looks like this, everyone's garden variety convex function, the epigraph is the set of points above the function line here. It's a set of points up here, including the function line itself. So if you've got a lower semi-continuous function, like I've got in this example, the epigraph here is going to include this piece of the vertical axis, whereas here it's not going to include that piece of the vertical axis. And so this set won't be closed. This epigraph won't be closed because this part of the line is not in the set, whereas everything else here and here is in the epigraph. Okay, and that turns out to be useful in many contexts, many optimization contexts. Okay, some other concepts that are useful when we're talking about minimizing these functions f. Coercive functions are those where as x goes off to infinity, the function value goes to infinity in all directions. That turns out to be a useful concept in making sure that your iterates don't run off to infinity. In fact, it guarantees that the set of minimizers is non-empty. There's this other observation that if f is strictly convex, then G has at most, the set of solutions has at most one element. Okay, there can be at most one solution. Here are some more examples. Here's a function that's coercive and strictly convex, and you can see it has a unique minimizer. Here's a function that's coercive, but it's not strictly convex, and there's a whole set of minimizers here, this whole range. And here's a function that's convex, but not coercive, okay, because in this direction it's not going to infinity. Like this could be e to the minus x, for example. This is a classic example of a function that's convex, that's bounded below, but it doesn't have any minimizers, okay? You can't point to an x that actually minimizes the function. Another important concept is strong convexity. Strong convexity is well, recall this is the definition of convex with a less than or equal to sign here. Strong convexity is where you can subtract off a strictly convex quadratic function and it will still be strictly convex, or at least convex, all right? So if I take the right-hand side here and subtract off a quadratic, strictly convex function that's 0 at the two endpoints, it'll still be quadratic, okay? It'll still be convex. So here's an example here. This is the function that I drew before, strictly convex. Now if I take that linear interpolant and turn it into a quadratic by subtracting this term, you can see it still lies above the true function, okay? And that turns out to have nice properties. As you saw in Francis's talk, you're able to say more about the convergence of algorithms under strong convexity than you can under just regular convexity. So strong convexity implies strict convexity, but not the other way around. You can have strictly convex functions that are not strongly convex. Can anyone think of an example in one dimension of a strictly convex function that's not strongly convex? X squared? No, that's strongly convex, because I can subtract half of x squared from it and it'll still be convex. But it's close. What's that? Exponent? Yeah, let's see, e to the minus x would be, or e to the x, yeah, that would be strictly convex but not strongly convex, right? Because as you go to minus infinity, the curvature goes to 0, that's true. Another one is x to the fourth. Okay, x to the fourth is strictly convex but not strongly convex. Okay, just a few notes here about composition of convex functions. If you take the max of a bunch of convex functions, it's still convex. If you take the composition of a convex function and an affine function, that is a function of the form ax plus b, that's convex. If you take a positive linear combination of a bunch of convex functions, that's convex. And importantly, this is why something I mentioned earlier, if you've got a set, a subset of Rn, there's this very important object called the indicator function, and that's the function that's 0 when x belongs to the set and infinity when x doesn't belong to the set, okay? So if C is a closed convex set, it turns out that this indicator function is a lower semi-continuous convex function, and that's a useful property, okay? Because it means that sometimes, well, we can write constrained optimization problems as unconstrained problems by simply replacing a constraint that x belongs to C, and I can take that constraint and replace it with just adding a multiple of the indicator function to the objective, and I've got an equivalent problem. And if the C is a closed convex set, that contribution to the objective is going to be a convex function. Okay. Now, suppose you've got a nice smooth function, one that's twice continuously differentiable, say. You can sort of see the convexity properties of the function by looking at the Hessian. Okay, so if f is a convex function, that means its Hessian is positive semi-definite everywhere. If f is strictly convex, then its Hessian is positive definite for all x. Okay? At least it's implied by that. This is a sufficient condition, not necessary. If it's a strongly convex function, you can say more. Its Hessian is bounded below. The eigenvalues of the Hessian are bounded below by some positive constant. Okay? That's what you need for strongly convex. So again, the Hessian can tell you about properties of strong convexity. All right, so let's go back to this problem of trying to recover the minimum cardinality solution of a linear system, AX equals B. So here the notation is a little bit different, and I've sort of relaxed the condition that AX equals B. I've replaced it with this condition here, that AX minus Y, or AW minus Y, is less than or equal to some threshold. Okay, so that's an NP-hard problem, it turns out. In general, computationally, this is very hard to solve. There's a very similar problem that's just kind of the flip of this, where you try to minimize the 2 norm, subject to the cardinality being below some threshold. That's also NP-hard, okay? Difficult problems. However, you can get away with, this is a very important principle, and in fact the central principle in compressed sensing, is you can often get away with replacing this cardinality, the 0 norm, with a 1 norm, okay? Under certain circumstances. And that turns it from being a hard problem into an easy problem. In fact, a convex problem. So you may have seen this picture already. This picture is literally on T-shirts that were produced a few years ago by colleagues at Wright that illustrate compressed sensing. So here we've got the setup I showed you earlier. You're making observations Y. There's an observation matrix A, and there's this unknown vector W. And in general, if you know nothing else about W than just the observations, it's impossible to recover the W that you really want. There's a whole manifold of W's or a whole subspace that satisfy, that give observations Y. Okay? And in fact, it's, as we said, we've shown that this is an NP-hard problem. However, you can show that you can recover under certain properties on the noise and the properties of A. You can, in principle, get the W that you're looking for by solving this problem, which is an NP-hard problem. All right, but Candace et al. Showed in around 2006, Candace, Romberg, and Tao showed that you can replace the 0 norm with a 1 norm. And you can suddenly turn this objective from being discontinuous and nasty into an objective that's convex, okay? Continuous, not only continuous, but convex. And you can get a convex optimization problem. And if A satisfies the right properties, you can actually get the same answer. Okay, so what sort of properties do we need A to satisfy in order for the substitution to work? Well, there's a whole range of different properties, but they're all basically closely related. Okay, so if you know, for example, that, okay, so one of them is the following, that if you take all possible vectors that have at most k non-zeros in them, and you form the matrix product of A times W for those non-zero vectors, then the norm of A times W can't be too much different from the norm of W, okay? In other words, there's a constant delta between 0 and 1 such that the norm of AW is not too different from the norm of W, okay? Difference captured by the constant delta. And this only has to be true for W that have fewer than k non-zeros. Another way to say this is that if I look at the matrix A, which has more columns than rows, and if I take out all possible column submatrices of K with at most K columns, okay? That column submatrix with at most K columns is not too far from having orthonormal columns, okay? So any collection of K columns out of A looks kind of like a slice from an orthogonal matrix. So that's a very strong property. It's a property that, fortunately, is satisfied by randomly generated A. So you can get A's that to high probability will have this property, if you just generate them by some random distribution. There are similar properties called spark and the null space property. This one's called restricted isometry. They're all NP hard. It's all difficult to check whether a matrix satisfies these properties. Naively, what you'd have to do is to go through all possible collections of k columns drawn from the total of n columns. So naively, you'd have to check all n choose k possibilities. That's obviously hard. And in fact, it's provably hard. All right. But as I said, fortunately, these things can be generated with high probability from random distributions. All right, so I've got a few slides here actually proving that for a randomly generated A, using a one-norm solution will actually give you the exact solution of the zero-norm problem. And I think this is a remarkable result. There are many other arguments that prove roughly the same thing. This is one of the simpler ones, I think. So I want to work through this in some detail. All right, so here's a problem we're trying to solve. I'm assuming there's no slack here, there's no noise, that the y's are exact observations of A times X. And the properties of A I'm going to talk about in a moment, exactly what we assume for A in this setting. So this is a problem we really want to solve, and now I'm just going to replace the zero norm with a one norm, and I'm going to talk about solving this problem. Okay? So let's suppose we know the solution of this problem. Let's suppose it's X bar. I want to find out if I can, under what conditions is X bar also going to solve this problem. Okay? To prove that X bar solves this problem, I have to show that if I take X bar and add any V to it, where V is in the kernel of A, that I'm only going to increase the one norm. Okay, I know because X bar solves this problem, I know that A X bar equals Y. Okay? And so any other feasible point for this problem is going to satisfy A times X bar plus V equals Y, which means that A times V equals 0. So to check that X bar is a solution of this problem, I just need to check this condition here. That if I add any element from the kernel of A to X bar, I'll increase its one norm. Okay? So this is what I'm going to focus on here. So this actually came from a paper by Yin and Zhang from 2008, early in the days of compressed sensing, and it was based on work about random matrices from the Russian literature, I guess, by these authors. All right? So here's the argument. This is what I'm trying to prove, again. So first of all, I'm going to define S to be the set of indices where the X bar I is not equal to 0, and Z is everywhere else. Z is the set of indices 1 through n where X bar I is equal to 0. Okay? So then given my X bar plus V, the one norm of that, I can just break it into two pieces. Because the one norm is just the sum of absolute values, I can take the S part of this vector, okay, which is just X bar S plus Vs, one norm of that, and add it to the Z part of this vector. Now the Z part of this vector, the X bar Z is equal to 0. Okay, so there's no X bar Z in this term. So this expression, which I'm trying to prove stuff about, we can break it down into that form. Okay, now I can use the triangle inequality. One of the fundamental properties of a norm. I can bound this term below by X bar S minus V, X bar S one norm minus Vs one norm. Okay, so all I've done there is use the triangle inequality. Okay. Now, what have I done here? Let me remind myself. So first of all, X bar S, the norm of X bar S is the same as the norm of X bar. Okay, because the rest of this vector is just all zeros. So I can just write X bar there. Okay, what have I done here? Well, I've said let me write VZ as V minus VS. Okay, V minus VS. And then I'll apply the triangle inequality again. Okay, so writing this as V minus Vs, and then taking the triangle inequality, I can write VZ1 as the norm of V1 as the one norm of V minus the one norm of Vs. So that's how I get that. Okay? Now I've used this inequality. There's an inequality. All norms are related, okay, when we're talking about Euclidean n space. So it turns out that the one norm of any vector in the set of n vectors of length n, is bounded above by the square root of n times the two norm. Okay? So I've used that inequality here to rewrite Vs1. I'm bounding it by the square root of k times Vs2. Because remember, S has only k elements in it. Okay, so I'm not really working in n space here, I'm just working in k space. Okay, S has only k elements. All right, so there's my upper bound there. Now, remember, I'm trying to prove that this is bigger than that. Okay, that's going to be true if this term in red here is guaranteed to be positive. So I will have achieved what I'm trying to do, showing that x bar achieves the minimum 1 norm, provided I can show that any vector v that's in the kernel of A has this thing being positive. All right? So just rearranging that a little bit, what I need is that for all v's in the kernel of A, I need the ratio of the 1 norm of v to the 2 norm of v times 1/2 to be greater than or equal to the square root of k. All right? Now, it looks like that's not going to be possible because all I can guarantee in general from when I'm dealing with general vectors of length n is that the ratio of the 1 norm to the 2 norm is between 1 and square root of n. Okay? That's all I can guarantee. That's not enough to guarantee this. Here I need it to be bigger than that. I need it to be, this ratio to be bigger than 2 times square root of k. However, I only have to restrict my attention to the kernel of A. Okay? I don't need this to be true for all vectors v and Rn. I only need it to be true for these. And remarkably, provided I choose A in a certain way, I can almost guarantee that this will be true. Okay, so what do we need? We need A to be chosen randomly. Okay? So if the kernel of A is in fact a random subspace of Rn, if you generate A by taking its elements to be sampled in IID from the normally distributed elements from mean 0 and variance 1, then you can actually show that to high probability, the ratio of the 1 norm to the 2 norm for vectors v in the kernel of A is bounded below by this number here. Okay? Now remember, in general, all we can assert is that it's bounded below by 1. But if you generate A in this fashion and take v in the kernel of A, you can show a much stronger lower bound. Okay? It depends on some constant times the square root of m. M is the number of rows in A, divided by the square root of the log of the ratio of n to m. Okay? So you can get a better lower bound, and that's good because we wanted a better lower bound. Okay? We need the lower bound to be bigger than 2 times root k. So in fact, if you can show that provided the number of rows in A is bounded below by this quantity, some constant times k times log n, that's enough to almost guarantee, to high probability, that this bound will be true. Okay? So this is the magic of compressed sensing, is that provided you have enough observations, it probably is still a lot smaller than n, you can guarantee that the solution of the 1 norm problem actually solves the 0 norm problem, the original, apparently NP-hard 0 norm problem. Okay? So let me show some pictures that sort of illustrate how this happens. So what I've done here is I've taken, I've got to remind myself, it's a couple of years since I did these experiments. But what I've done is taken vectors in R7. Okay, this is a 7-dimensional space. Unfortunately, it's hard to depict anything bigger than 3 dimensions. But I've taken vectors in R7 and I've generated a random matrix with 4 rows. So the kernel of A is going to be a 3-dimensional space, okay, which is something I can draw a picture of. So what I've done is generated this A randomly in the same fashion that I showed you by picking its elements to be normally distributed 0, 1. And I'm plotting here the unit ball in the kernel space. So I'm taking all vectors in the 3-dimensional kernel with a 2 norm of 1. And I'm color coding it according to this ratio of the 1 norm to the 2 norm. Well, the 2 norm is always 1, so I'm just plotting the 1 norm. And I'm color coding it so it's blue if the 1 norm is close to 1 and red if it's close to the upper bound of square root of 7. You can see from this picture that there's no blue, okay? In other words, it's well away from its lower bound. There's quite a bit of red. In other words, it tends to be closer to its upper bound. And that's exactly the property that we want. Okay, we want it to be away from its lower bound. We want it to be bigger than 2 times square root of k. And that's what we're seeing in this picture. Okay? This is what happens when I go even more extreme. When I take the 20-dimensional space and generate A to have 17 rows. Okay? Again, I've had to choose enough rows that the kernel is only a 3-dimensional space. And again, if I do that same plot of what is the 1 norm versus the 2 norm over the kernel, you can see that it's almost always, it's almost all red. Okay? So in other words, it's much closer to the upper bound than the lower bound. And that's the property that we need for compressed sensing to work. Okay? So there are many other arguments that are made. They have, I'd say, kind of a similar flavor to that show that the 1 norm is a good proxy for the 0 norm or for the cardinality count in many circumstances. All right, so that was sort of an idealized situation. Usually we're dealing with noise here. Here is kind of a depiction of what you get when you do compressed sensing with the 1 norm. So here we've got a combination of a fitting term, which is a 2 norm, and the 2 norm is appropriate because I'm assuming here that the noise is IID Gaussian, so it turns out that the 2 norm is a good way to measure the fit between the observations and the predictions, and then the 1 norm is doing its job as the regularizer here. And you can show if you've got a code that minimizes this function, and provided you choose the lambda appropriately, that from a set of observations y, you can actually recover a sparse solution that looks a lot like the original data vector. Okay. So this principle has been around for a while. In statistics, people are interested in things like basis pursuit denoising. There was this thing called lasso that dates to 1996. It came up in the context of feature selection, where you're trying to find which elements of X are really important in predicting the outcomes Y. Again, trying to look for sparse X that satisfy AX equals Y approximately. It's been widely used. It was discovered in many other areas. The use of the 1 norm to induce sparsity was discovered much earlier than its kind of rigorous derivation in compressed sensing. And there's a whole bunch of citations here where people in other fields, radio astronomy, actually geology and geophysics is one of the first places this came up. When I was writing my thesis back in the mid-'80s, I had a chapter on geophysical inversion, and people there in this field were already using principles of using the 1 norm to induce some sort of sparsity regularization. Okay, so why does it yield sparse solutions? I've sort of explained that a little bit in that idealized example, but here are some pictures that maybe build the intuition as to why the solutions that you get from using a 1 norm are sparse. Going back to those unit balls that I drew earlier for the 1 norm and 2 norm, suppose you solve this sort of a problem. You try to find the W that minimizes the fitting function, subject to the 1 norm being below a certain threshold. So the blue pictures here are the contours of this quadratic function, okay, that tell you the fit. And this is going to be the constraint in this particular formulation. So you can see here that there are many places that I can place this quadratic function so that its constrained minimum will be at one of the corners of this square. Okay? So if the quadratic, of course we're kind of lucky here, and the quadratic has circular contours. More generally, we'll have elliptical contours. But there are many situations where the minimizer will be exactly at one of the corners. Of course, there are others where it won't be at a corner, in which case you won't get a sparse solution. You get a solution with 2 non-zeros. However, if you've got the 2 norm here, you'll almost never get a solution that's at one of these 4 corner points, okay, at one of the 4 points where you've got a sparse solution. It will generally be somewhere on the surface of the ball. And you have to be very lucky for it to land at one of the corners. Okay, so a little bit more detail on why L1 yields sparse solutions. All right, if we just idealize, if we break this down to just a single variable, okay, if we have a combination of the 2 norm and the 1 norm just in a single variable, you can write down in closed form what the solution of this problem is. So given the y, it's now a scalar, the solution of this problem, finding the w that minimizes this, is the so-called soft regularizer, okay? It's given by this solution. If the y has absolute value less than lambda, the solution is 0. If it's bigger than lambda, then the solution is y plus or minus lambda, depending on the sign of y. So you can see that when y is close to 0, the solution to this problem, it actually pulls it down to 0, okay? And so and that's how it's inducing sparsity. If it sort of gets close to 0 in this prediction, it pulls it exactly to 0. That's what the one norm does. So here's a picture of what that function is doing. There's a whole range of values here where it actually goes to 0. Whereas if you're using the 2 norm here instead of the 1 norm, if you replace this with the 2 norm, again you can solve that in closed form, but the solution is just a scalar times y. Okay, so it'll just shrink it towards the origin. But in general, the sparsity of this solution, of the w here, is just going to be the same as the sparsity of y. Okay? All right, you can also write down what the solution of this problem is for the case where you've got the 0 norm here. Not really a norm, but suppose you have the cardinality here. You can write that down as the hard thresholding operator, okay? And that operator, is, again, is just 0 if y is less than square root of 2 times lambda. And it's y if y is bigger than square root of 2 times lambda. So if I draw a graph of that, of the hard thresholding operator, it doesn't look too much different from the soft thresholding operator, okay? Out here when y is different from lambda, it looks basically the same. It's just that the one norm has kind of compressed it a little bit towards the x-axis. But in this range here, it's exactly the same, okay? So this is one kind of, another indicator that this is a pretty good proxy for that. Even though the problems we have to solve, if we use this guy, are convex, and the problems we have to solve if we use this guy are combinatorial, okay? Okay, a little bit more, and I'll say more about this, I think, in the last talk today. When we're doing image processing, which I know a lot of people here are interested in, very often images are really sparse objects in disguise. Okay? There's a sort of inherent sparsity in images that is not always apparent from just looking at them, you know, as a collection of pixels. So often you can represent images, for example, using a wavelet basis. And sometimes if you choose the basis appropriately, if x here is just the set of pixels in the image with, you know, the value proportional to the grayscale intensity of the pixel, then you can sometimes represent the pixel by pixel count as the wavelet basis times some coefficient vector. And often you'll know that you can represent the image adequately as a combination of a fairly small number of wavelets. In other words, you're looking for a coefficient vector w that has a relatively small number of elements. Okay? So you can reformulate the problem in terms of w and seek a sparse solution. That's one way to deal with this. Okay? And so if you've got a problem like this in image reconstruction, you can write, okay, so I've rewritten the problem here in terms of the wavelet coefficients. Okay? So in other words, I get the actual image by taking the coefficients x times w, which takes me from the wavelet domain into the real domain, and then there might be something that happens in the real domain, in the pixel domain, like there might be some sort of convolutional blur that's going on. And so the observations I'm making might be some blurred picture of the true image. And so very often I can recover a much sharper image by solving this regularized problem where I impose some sort of sparsity on the wavelet coefficients. So this is an actual picture of a blurred image where we've solved this problem and recovered a much sharper image from it. Of course, here we assume that we know what the blurring operator is. Okay, and that's not trivial in applications, figuring out what the blur operator is. But here I've assumed that that's known. Here's another application to magnetic resonance imaging, and here again the trick is to work in the right basis, to impose sparsity in the right basis. So here we've got a composition of a wavelet basis that takes me from wavelet space into real space, into frequency space. Then there's some sort of DFT going on, and then there's a binary mask. So I think this is, I don't know much about this application, but I believe this is typical of MRI. And so again, you've got some sort of original image. In the DFT domain, the acquisition, the data that you're actually observing looks like this. And then when you do the reconstruction using this with an appropriate value of tau here, you get an optimal x, an optimal set of wavelet coefficients. You multiply that by the wavelet basis to get you back into real space, and you get this image. And you can, it's actually not obvious in this resolution what the improvement is. I can't see much difference. Maybe you can from a distance there. But believe me, this is nicer than that one. Okay, you'll have to trust me on this. Oh, I see. Okay. Oh, good. All right.
If you improve the original.
Yeah, that's true. That's true. Okay. Yeah.
Make a pause of 2 minutes.
Pause of 2 minutes?
Yeah, so that you can
Oh, I'm sorry. Yeah. I went over the break. Yeah. Should we stop now briefly? Yeah, let's have a 2-minute break. Yeah, this is great. Sorry about that. I should have stopped earlier.
You started 10 minutes late, so or is
I've got about
continue?
I've got about 20 minutes left in the session.
He started 10 minutes late, so we have 20 minutes left. So
Is anyone faint? People in the middle should get to say because they're probably the warmest.
one who's already sleeping.
Let's make 2 minutes pause with fresh air.
Right. Okay, now I can get a drink too. Do we have water? Okay. Morning.